So the next speaker is Marco Sangiovanni Vincentelli, who will speak on degenerate automorphic forms and Euler systems. So please.
Thank you very much, Professor Tilwin, for the introduction. And let me reiterate Chris's remarks that I'm very happy to, we're very happy to give this lecture series. And I'm very sorry that I couldn't be there in Bangalore to give this series of talk. Unfortunately, my visa got denied twice. But anyhow, so the purpose of today's lecture will be actually to answer in sort of more detail a question that Professor Hida asked last time to Chris, that is to clarify the scope of the method. So, and basically Chris last time gave a series of examples, and how do you hunt for new examples? Okay, so it's sort of a semi-axiomatic treatment because we don't know yet whether this is really the condition that I will put or really necessary, or just as of now restrictions. All right, so let me start by just giving the plan of today's lecture. So the first, as I said, I will give a roadmap of the method. So sort of what are all the key steps, and then I will revisit briefly what Chris did. So this is the baby case of the cyclotomic units Euler system. So for GL2, just I will recast it what Chris did in the framework of the roadmap, and then I will give sort of a duality picture between pullback Euler systems, what I call pullback Euler system, versus push forward Euler systems. Okay, so I will explain a little bit what do I mean by this, and then I will end the talk by sort of saying what's ahead in my next 3 lectures. Okay, so let me start with the number 1. So that is the roadmap. So the first thing to be introduced is, so I will consider rho GQ in GLN. For simplicity, I will assume that this has coefficients in QP so that I don't have to worry with coefficients. And also the field is Q, but obviously there is something over more general number fields. But let me just assume that we're interested in a representation of the Galois group of Q. And this is continuous and geometric in the sense of Fontaine-Mazer, but it would be nice to just assume that, so rho appears in the cohomology, say in the Tal cohomology of some variety y with some twist, let's say d, as a quotient, sorry, this QP. And then inside rho, there is a natural lattice T, which is just the image of the cohomology with integral coefficients. Okay, and so this lies inside. And so I will assume that Y is the Shimura variety of some group H. And so rho, there is an automorphic representation, pi is by global Langlands, pi automorphic representation of H of A. And I mean, rho is the expected Galois representation that appears in the cohomology of Shimura varieties according to Kottwitz's conjectures. Okay, so this is rho is the Galois representation we want to build an Euler system for. Okay, and so one motivating theme of Chris's lecture yesterday and what he said is that he was motivated by the presence of an automorphic integral computing the L function of rho, or in this case pi. So key feature. So I will assume that there is a group G, a reductive group G, which contains H. So we will see later when the roles of G and H are switched, this will be the push forward method. So there is a reductive group G containing H with a Shimura variety Y, the Shimura variety of G. And sorry, here I think I called it Y. Let me call it Z just to be consistent with my later notations. Okay, so both G and H have Shimura varieties, and I will assume that there is a family for any, so for any Dirichlet character chi, there is big pi of chi, an automorphic representation of G of A, and the pairing, so I will call this by big P, from pi tensor pi chi to C, that computes the L value. So in some specific sense. So I will just think of it in terms of in some geometric terms. So I have a small vector v in pi and a big vector v in pi chi, and I will denote this pairing as v restricted to z paired with z on z. So this is the small Shimura. And this period, this pairing closely related to the L function of pi twisted by the character chi. So the family pi chi is the family of degenerate automorphic forms. So in Chris's talk, this would be in GL2, the family of GL2 Eisenstein series, and you can choose on one factor of the torus of GL2, maximal torus of GL2, a character with the correct parity condition. So, but we will see many examples where I will say explicitly what this big period P is. Okay, so as I said, examples. The main example I will focus in this lecture series will be Eisenstein series, but also theta series. Okay, these are both okay from the setup. And now here comes the most sort of limitation, numerological limitation of the method. And so if the infinity part, if pi infinity contributes to degree m, then for all chi, pi chi infinity needs to contribute to a degree n plus 1, okay? One more. So this, in practice, what does this mean? Usually, pi contributes to middle degree, and also pi chi infinity both contribute to middle degree cohomology. So the key numerology assumption implies that the Shimura variety for the small group inside the Shimura variety for the big group, I'm forgetting here level structure for simplicity, should be codimension 1. Okay, so this is sort of all the example basically that Chris mentioned all fall into this category, where the Shimura variety of the small group inside the Shimura variety of the big group is codimension 1. Okay, and okay, so once you have this setup, so you have your Galois representation you're interested in, an automorphic representation, and with the Satake parameters that match, and you have an integral representation of the L function of pi with respect to an integral or a pairing with some other automorphic representation on G, big pi chi for any Dirichlet character chi. And if you assume this key numerology assumption, then we're in business to try to construct the Euler system. Okay, so now I will explain the method in the following diagram. So as I said, the starting point is this is actually, you should look for in the literature for the construction of a p-adical function. So here you go, here you have the construction of p-adical function for rho or pi, and should be by interpolation of the period integral p. Okay, so p-adic interpolation of whatever this period integral p is. And so here you will have a p-adic interpolation of the family attached to pi chi, but restricted to the small group H. Okay, so you have a p-adic interpolation or a p-adic family of that interpolate all these pi chi's, and moreover, you have an interpolation of the period integral. So that's sort of what you're looking for in the literature for the construction of the p-adical function. And now you're hoping that the Euler system that you construct with our method would see this p-adical function in the explicit reciprocity law. Okay, so the first, now you have this, and now you go in the other direction. So you specialize to appropriate classical point. And so this should give you an analytic de Rham class on the big Shimura variety, the one for G. And then you should find a geometric reason sort of why pi chi is degenerate. And that should allow you, plus rep theory, that should allow you to upgrade the analytic class that you get from this degenerate family to an geometric étale class with abelian, sorry. So you upgrade it to étale class with abelian GQ action, or GF for some number field. Okay, and then the last step is you're hoping to get an Euler system by looking at relative cohomology. So this is the step that Chris explained before, and this is where the numerology assumption comes into play. So here you build a lot of extension classes, and then you patch them into an Euler system. And then the last step is p-adic Hodge theory. Also known as, this is the explicit reciprocity law part, which is a subject in and of itself. So Chris talked a bit about the explicit reciprocity law yesterday, and how it comes about from the very construction of these étale classes. So they should come with the de Rham comparison, a p-adic de Rham comparison. Okay, so now let me explain what I will talk about in this lecture series. So this will be mainly focused in this section of the diagram. Okay, so going from the analytic de Rham classes attached to classical automorphic forms where you can write explicit expressions for, and then what is the process? What is this arrow? How do you upgrade to étale classes on which you understand the Galois action? And I will also talk maybe a little bit about how do you prove the norm relations for the Euler system. I will not talk about this part, which I view as a separate, almost separate field, and especially I will not talk about the explicit reciprocity law. Okay, but I will go into quite some detail into how you go from here to here, and especially how do you prove integrality. Okay, so maybe then let me review now Chris's example and what each of these arrow means. But before, are there any questions about sort of the general setup? Okay, so if not, then, so number 2. Okay, so now I'm revisiting the examples with respect to this point of view, so this diagram. So A, so the cyclotomic units. This was Chris's talk. So who is the group H? H is just GM, and G is GL2. Pi chi is the family of Eisenstein series, so I will give directly what the specialization is. So from the Borel of GL2 of the modulus character to the 1/2, and then chi tensor 1. So this is family of usual weight 2 Eisenstein series. And then this, the Shimura variety for GM, I see it inside the Shimura variety for GL2, or rather it's compactification. So this is the boundary. Oops. This is inclusion of the boundary. And the representation that I'm interested in is, I almost forgot to say, is ZP1. And the little pi is just the trivial representation, okay, of GM. And so there, what is the period integral? is, as Chris said, is the evaluation at two cusps, at the difference of two cusps. Okay, so then let me go back to this diagram. So here we said we have our usual ordinary family of GL2 Eisenstein series. This is if you take the new vector and chi is ramified at P, then it's ordinary. And you specialize, so to weight two classical point, you get analytic de Rham classes. These were the classes that Chris denoted by omega chi in his talk. And the process of going from these analytic de Rham classes to étale classes with abelian GQ action was using what is called the Manindrian field principle, which is basically saying that Eisenstein series do not interact with the Galois action on cos forms, and so they're completely determined by their image to the boundary. And so you can read off both the rationality properties and the Galois action from the constant term. Okay, so this was this arrow here. And then the interpolation, the p-adic interpolation of P and the evaluation at two cusp was done by Katz. And even before, in maybe less axiomatic way, by Serre. This is Serre's construction of the p-adical function, which is the Kubota-Leopold p-adical function. Okay, so p-adical function with the construction by Serre and Katz. Okay, so this was the baby case. So, and now let me revisit a few more examples in Chris's list. So there was also the elliptic units. So this is the case where, so we're interested in the Galois representation ZP1, but not anymore over Q, but with an action of GK, where K over Q is quadratic imaginary. Okay. So now what are the groups? Well, H is going to be, say, GO2 for the norm form of K. So and then inside GO to 1, which is just another way of saying that it's GL2. So this is the group G. So I'm interpreting this with respect to GO2 and GO2 just because of Prasad's remark yesterday that all these examples come from GGP, really. So this would be orthogonal GGP. And so you'd consider these groups, and then the Shimura variety for H. So this is just the Shimura variety for GM over K inside the Shimura variety for GL2 is just the inclusion of CM points inside CM points with respect to K inside the Shimura variety for GL2. The family pi chi is as before. And the period is just the evaluation on linear combination of CM points. And this is very much related to what we saw yesterday in Thiluin's talk with Damerel's formula. The fact that when you integrate on CM points an Eisenstein series, so this I will be very sloppy and say that this is the L function for against the character chi. This is the L function for chi. Okay. So I will refer you to the very precise statements, even over a totally real field that Thiluin gave yesterday. But so, and then the p-adic interpolation, again, if I go back to this diagram, the p-adic interpolation of Damerel's formula was done by Katz. Okay, so this was done by Katz, and now you specialize again to weight 2. The process of constructing the étale classes is exactly the same as the one that Chris mentioned, and now you're just considering a different relative cohomology sequence. Okay, so relative cohomology sequence. But the origin of the classes are the same. So this is the degenerate family is the same. So maybe let me also make a remark that also in the classical way of getting the elliptic unit order system and the cyclotomic elliptic unit order system, the process is still the same. It's just that for cyclotomic units, so evaluate or take residues really, a modular unit at a cusp. And for elliptic units, it's just again not this time is really evaluate a modular unit at a CM point. Okay, so and indeed these Eisenstein series, this weight 2 Eisenstein series, where did here, these weight 2 Eisenstein series, which from the automorphic point of view are this representation, they are the D log of these modular units. So of course we're not really, of course this is the same order system that you would get from the classical perspective. We're just boycotting modular units because we don't have modular units available for more sophisticated Galois representations. Okay, so now let me finish the sort of collection of example by giving what Kato's order system. So here the Galois representation is rho f, rho of rho f, where f is a cuspidal eigenform for GL2. And what Kato does is that now the degenerate family lives on GL2 times GL2, and it's just the product of two Eisenstein series. So it's p chi times p chi inverse, essentially. Okay, this is for central character reasons. So this is p chi times p chi inverse, so a product of two Eisenstein series. And so now what is the Shimura variety is just the group H is GL2 embedded diagonally inside GL2 times GL2. So from the point of view of GGP, this is GO to 1 inside, say, something like G of O to 2. GO to 2. So it's the Shimura variety of G embedded diagonally in the Shimura variety of GL2 times the Shimura variety of GL2. So this was in my notation previously. This is my Z inside my Y. So diagonally. Okay. And so what is the period integral? P is the Rankin-Selberg integral. And the p-adical function, the construction of the p-adical function is due to Hida, or in this way to Hida. So I hope that now the picture is becoming clear in what do we need. Let me just notice that in all these examples, as I mentioned before, all the representation appear in middle degree. So this, for example, is dimension 1. This is dimension 2. So the codimension is 1. And here as well, you have 0 and then 1. So codimension 1. Sorry, this dimension 0 and this is dimension 1. So again, codimension 1 and the same thing for the boundary. Okay. So now let me just state the new examples. So in this, so the main one that I will treat in this lecture series, I will talk about it tomorrow, will be the Siegel case. This is, so I will be interested in rho is now the at zero of rho f, let me say twisted by 1, where rho f is as before, the f is a cuspidal eigenform for GL2. Okay, so this is the Galois representation we're interested in. And so who are the groups? So now the groups are GL2 over that GL2 inside which group? Well, GSP4. This is my G. And now who is the degenerate family of Eisenstein series? This is pi chi is Siegel-Eisenstein series. Eisenstein series. This is a Siegel-Eisenstein series. So, and what is the period integral? So P is the doubling integral. It's just a doubling integral, where when you integrate a Siegel-Eisenstein series, and then you have f times f bar, and you integrate over GL2 times GL2, then you get the L function of at 0 of f. And so who constructed the p-adical function? From this point of view, for really any GSP4 and so for any, from this point of view, Zheng Liu the p-adical function that we need, or rather the formula for the p-adical function that we need. Because there is prior work of Schmidt and Hida that construct sort of the same p-adical function, but it's not the formula that we want. Because of this method, we really want a formula that where the Siegel-Eisenstein series that appears in the period interval appears, and not something else. So this is also an important part of the method in the diagram that I drew before. Okay, so this will be the example. So this is the example of next lecture, where I will treat in detail how do you upgrade this Siegel-Eisenstein series to something more arithmetic. Okay, and then let me just mention briefly that as Chris said, you can play the same game for UN1 inside UN plus 1, and so this should give an infinite family of Euler system. But maybe if I have time, I will say what the difficulties are in tomorrow's lecture. Which this case showcases some new difficulties that do not appear in the Siegel case that I said before. And in the last lecture, I will also review, well, the example where rho, the Galois representation we're interested in, is rho f, but instead of an action with GQ, I consider it with an action of GK, where K over Q is quadratically imaginary. And now the degenerate family of Eisenstein series, sorry, of automorphic form, is a theta series. So theta of chi, a Hecke character of k, product my usual GL2 Eisenstein series. Again, the period integral is the Rankin-Selberg integral. And the p-adical function was constructed by Ryu and Hida. Okay, so then to go back, this will be the examples I will treat in detail. So this example here for the construction of the arithmetic version of these automorphic representations and this Siegel case. Okay, so maybe let me stop 1 minute to ask if there are any questions. Okay, so if not, then let me go to number 3 and talk about push forward versus pull back. So I explained so far I explained the pullback picture. So this means the degenerate family is on the big group. Okay. Now let's take the point of view when, and there are lots of examples, when the degenerate family lies in the small, so lives on the small group. So in my arrows here, I had the p-adic family. Here I had my p-adical function. Then here I had the specialization. So analytic class, and then I went to étal classes, and then here I had the order system, and then here I go back with the explicit reciprocity law. So what changes? Well, here really, in this part of the diagram, so, I mean, it's a bit, nothing changes. So you just switch the role of G with the role of H. So the construction of the classes is independent from whether you're working on a small group or a big one. It doesn't yet know about who the little pi is, okay? But, so the difference comes into play here. So in the pullback, so what I mean by here is the difference comes about in this arrow. So in the pullback situation, I was considering relative cohomology of the pair ZY. But here, in the push-forward case, one should consider rather the cohomology of the open variety. So say y excised variety rather than open, excised. So y, but without z, okay? And then also the explicit reciprocity law. Now, since you've pushed forward, you most likely will have to leave the realm of just classical Hida theory and enter higher Hida theory. But I'm not in a position of, talking much about explicit reciprocity laws in the push forward case. This is sort of the expertise of Lufter-Zerbis. Okay. Using higher Hida theory. But I just wanted to discuss the role of the arrow, this arrow. So when you switch from relative cohomology to just the cohomology of the excised variety. So what do I mean by this? So Chris mentioned that he wasn't going to talk about, say, the Euler systems of Higner points, but one way of seeing how, at least in a modern perspective, how do you construct the Euler system of Higner points is with the cycle class map. So if you have z inside of y, then you can consider the constant function. So this is in the H0 of ZZP. And this, by the Giessen isomorphism, is just the H2C with supports in Z. So let's say that this is smooth pair. And this is the Giessen isomorphism, that this is just, and could I mention C? I forgot to mention. This is just the cohomology with supports in Z of X of ZP twisted by C. But there is a long exact sequence and so this is the image of the constant function in here is what usually people call the class of Z. And there is always a long exact sequence that is of the following shape. You have the cohomology of Y with, let's say, ZPC coefficients to the cohomology of, let's say that, let me write U is Y without Z. And so y to the cohomology of u, this is just pullback. And then you have the cohomology with supports in z. Okay, so this is +1 actually. Okay, this is the long exact sequence. And so if you take the bullet to be 2c minus 1, you get 0 goes to h2c minus 1 of y ZPC goes to h2c minus 1 of u ZPC, which goes to h of 2c with support in z of x ZPC. And here you have your class of z. So if z is null homologous, this means it maps to 0. So this is all geometric étale cohomology, by the way. So
what is x?
X is y. I'm sorry. Thank you. Yeah, x is y. Yeah, so if z is null homologous, so this is q bar. If z is null homologous, i.e. class z maps to 0 in h of 2c of, again, x, y of ZPC, then you get an extension which is going to look like h of 2c minus 1 étale of yq bar ZPC goes to some e, which goes to ZP times the class of Z. And so E is just a submodule of the of the cohomology of the X-size variety. Okay, and the extension class of E, was proven by Janssen, is the Abel-Jacobi, the étale Abel-Jacobi image of the null homologous cycle Z. Okay, and in the Higner point, so the cohomology classes in H1, say K of H1 et al. Of the modular curve coming from Higner points are constructed in this way. Okay, meaning in this way, I mean by the étale Abel-Jacobi map of a appropriate linear combination of Higner point with a multiple of the infinity cusp, say, so that you have a null homologous cycle. Okay, so this is really a motivation for why you would consider the excision long exact sequences, because it's very much related to the Abel-Jacobi map, and so it should verify similar functorial properties, etc. And it does, and it works quite well. Okay, but so then this allows one to motivate the use of relative cohomology in the following way. So you always have in the derived category, so the setup is always the same. So let me say that J is the inclusion of U inside Y, which contains Z. This is iota, and this is J. So iota closed immersion, and so U is Z, sorry, it's Y without Z. Okay. So you always have the following diagram of functors, exact term. So for any étale sheaf F on Y, so F goes to F, goes to R iota star I pullback of F, and the excision sequence, at least one wire property, is essentially, so this goes to +1, is essentially obtained by taking R hom of F shriek of ZP when F is ZP, and who is F is just the map from Y to spec of Q bar. It's just the structure map. Okay, so the excision sequence is taken by taking R hom of this and then derive global sections. But this sequence, when you take, so in this sequence star, if one takes R gamma of Y et al. Of the sequence star, one obtains the defining long exact sequence, which is H bullet of Y relative to Z, Y relative to Z with coefficients in ZP, goes to just the cohomology of Y, goes to, and this is by pullback, the cohomology of the closed one. Okay. So the push forward, this functor is essentially the functor that gives you Poincaré duality. So you see that the excision sequence and the relative cohomology sequence, so push forward, pull back pictures are related by Poincaré duality, at least in a derived sense. Okay, so I hope that this this paragraph was there to motivate where does this use of relative cohomology, this idea, comes from. It just comes from the fact that in the classical way that one would construct classes is by taking Abel-Jacobi maps of something that we have pushed forward. But so since now you're in the pullback situation, well, it's natural to consider the dual sort of sequence than the excision sequence, and that dual sequence is the relative cohomology sequence. Okay, so this was just to motivate this point. And so now let me end today's talk by saying what's ahead. So in the next lecture, I will talk in detail about the construction of arithmetic Siegel-Eisenstein classes on the Shumor variety for just before. So this was, recall the example for rho is the adjoint. And so the picture is that you have the Shumor variety of GL2 times the Shumor variety of GL2 over that inside the Shumor variety for just before. And I will do all the construction except integrality. So in 2 days, so lecture next, so this one, and the next lecture, I will talk at length about integrality. So this will be the most technical talk. So this will be really about p-adic Hodge theory, and more precisely integral p-adic Hodge theory. And so this is the key map or the key ingredient that allows one to sort of relate certain vectors in the Tal cohomology with a canonical Galois to certain modular forms, classical modular forms. So to pinpoint the RAM comparison of such a Tal classes. Okay, so this is really one of the most important points. And then in the last lecture, I will treat the example of how do you apply these ideas to construct theta series. And I will sort of motivate why one would like to go beyond Eisenstein series. And that will be related mostly because of the numerological, key assumption where you need this numerology to match. And so basically but Eisenstein series need always something non-proper. So you always need a boundary. But when you, for example, if you want to work over a totally real field, then you would want to have the correct numerology, you would want something compact at certain places and non-compact. So instead of working, say, over a Hilbert modular variety, you would want to work over a Shimura curve. But there are no Eisenstein series on the Shimura curve. But there are theta series. So this is sort of the motivation on why to study this question of theta series. And also it gives some new applications for Iwasawa theory of a modular form F, but over a quadratic imaginary field K. All right, so I think I'll stop here, and thank you. Yeah.
So are there questions, comments?
Hi, Marco.
Hello, Eric.
So I wanted to ask if in the construction you can construct the Euler system in families as well. Like you take a Hida family of modular forms.
Yes. Yeah. So that's because of sort of so then you have to choose your sections at P correctly for on the Eisenstein series side. But yes, you interpolate everything from weight 2.
Okay. Okay. Thank you.
Hi, Marco.
Oh, hello, Ashay. Hi.
Just a vague question. In the dual picture, like some of the relation to like explicit reciprocity law becomes a little more direct. Like, is there some philosophical reason?
So you mean more difficult?
Maybe a little more direct.
I think it becomes more direct when you're looking at cycles, maybe. But I would say it becomes more difficult because you need a p-adic theory of higher coherent cohomology classes.
Or like the dual to relative I was asking for the relative cohomology.
Why is it simpler?
Yeah. Yes. Yeah.
Because everything is holomorphic. In these integrals, so in the pullback integrals, from the Archimedean perspective, so from the pullback, if you have E, say an Eisenstein series against F is something non-zero and E is holomorphic, this has a tendency, to imply that F is also holomorphic. So everything is H0, so everything becomes simpler. Instead, in the push forward, this is precisely not the case. For example, in so this is Skinner, Piloni, and Loeffler-Zerbes, where they construct the p-adical function. This is the Duke paper for just before. You have the Furusawa, or I think Furusawa, I forget exactly who this integral is due to, but you have two Eisenstein series, E1, E2, this is GL2, and this lives on GL2 times GL2, and now you restrict an F on GL2 times GL2, where F is automorphic form on GSP4. Then F cannot, so if E1, E2 are holomorphic, but if F is holomorphic, this is 0. You need something that contributes, I believe, to the something coherent H2. So you need to, for the p-adical function, you need to somehow see these higher coherent cohomology classes. And this is much more difficult because, for example, one way to do the explicit reciprocity law in the case that Chris treat, even in the case of GL2, is by restricting to the ordinary locus. But so the ordinary locus is, at least for the minimal compactification, it becomes affinoid, but this has no higher coherent cohomology. So you cannot see these classes just by restricting to the ordinary locus. You have to look at something larger.
Yeah, thanks. And can you also just briefly mention where does this codimension one like kind of comes in, like the key role played by the codimension one?
Yes. So the codimension one hypothesis is that, so if you assume that both appear in middle, little pi and big pi comes just from the fact that you have this exact sequence. So so y relative to z, let's say zp, to m of x, y again, y with zp goes to hm of z, but okay, so this is m, and then here you have hm minus 1 of z. And here you have hm minus 1 of y. So you would hope that here you have your class omega chi. Your class omega chi, you hope that it maps to 0 on the right-hand side, and the Galois representation is not killed by the image of this hm minus 1 of y. And so then in order to build the extension, you get something where you get, so maybe this has a map to rho, you get 0, rho, and then a subquotient of relative cohomology, and then here you get, zp, if this maps to 0 here, okay? And this map passes to the quotient. So you get such an extension like this. But so you see that the Galois representation that you're interested in and the class coming from the degenerate automorphic form need to be off by 1 degree. Here you get m minus 1, and here you get m. Otherwise, if they are further apart, you don't get an extension.
Thanks.
And maybe let me notice that in the case of the push forward, the numerology is a little bit different. The code twice the codimension plus 1 or minus 1 enters into play. But yeah, anyhow, this is all numerology. Yeah.
Yeah, thanks.